In our most recent video, we introduced the notion of parametric equations, and we motivated their use by introducing a curve called the cycloid that we were able to express in terms of parametric equations without a whole lot of difficulty, and for which the equations turned out to be relatively straightforward. Today, we would like to continue our discussion of parametric equations by providing some examples of several pairs of them and talking about how to draw graphs that are described by these equations. We're going to begin by looking at an example that you are really familiar with. Let's go back to the whiteboard. We're going to start by talking about the circle. And we want to notice that we can describe the equation of a circle. This is a circle with radius 1 centered at the origin. Right? We can describe its equation by simply, well, what is an equation? It's a description. It's a truth. It's an algebraic expression which captures a truth about an object. In this case, it's going to capture the truth about a circle, the truth being that every point on the circle is the same distance from the center of the circle. So if I draw a line from the point down to the center, of course, I get a line of length 1. From there, I'm going to drop an altitude down and form a right triangle, and observe that the height of that triangle is the y-coordinate of our point. The bottom leg of our triangle has length, which is the x-coordinate of our point, and we can just read off the Pythagorean theorem in terms of the symbols that are adorning our picture here. So x squared plus y squared is 1 squared, 1. So x squared plus y squared is 1 is the equation of our circle. But there's another thing that we could have done here. Another way we could have looked at this, and that is by recognizing that if we identify the angle that is defined by this hypotenuse against the positive x-axis, call it theta, then let's see, the adjacent side of that angle, which is x, divided by 1 is going to be the cosine of that angle, right? So that tells me that x divided by 1 is equal to the cosine of theta, right? And similarly, y divided by 1 is equal to the sine of theta. And what we have then is a pair of parametric equations which describes the circle, right? We know that cosine squared theta plus sine squared theta is always 1. And so I can translate from that x squared plus y squared is always 1 whenever x and y are defined in this way. All right, so that's using a familiar example to show that we kind of knew something about parametric equations all along. Let's look at another similar example. Actually, it's the same example, but we're going to go in the opposite direction, right? So what I have here is the graph of cosine, which is describing x, and the graph of sine, which is describing y. And I want to talk about how we can go from these graphs to the graph of the circle that we have up here. And I like to describe this in terms of, I don't know, etch-a-sketch geometry. Right, I'm looking at two different, I'm looking at X values, that's describing horizontal distance, and Y values, that's describing vertical distance. And so I'm starting at some point, let's see, here, X is 1 whenever theta is 0. So this axis now we're thinking of as describing the values of the parameter theta. So whenever theta is 0, my graph here tells me that the X value is 1, right? So X is 1 at the same time that Y is 0. So 1 comma 0 is going to be a point on my graph. So that point right there is going to be a point on my graph. And then I'm going to, so this tells me that my X values are going to get smaller. So, right, my X values are going to move in this direction at the same time that my Y values are getting bigger, right? So in kind of an Etch-a-Sketch geometry, I'm going to be turning my X knob. I guess I'm going to be have to decide which knob describes which. I'll let the left knob describe X. So I'm going to be turning it in a reverse direction while I'm increasing the knob on the Y's, and that's going to. So let's see. I'm going from 1 to 0 in the X direction while I'm going from 0 to 1 in the Y direction. And so that's going to have an effect of doing something like that on the interval between theta being 0 and theta being pi over 2. Now, notice, how did I know to make my curve go that way rather than this way or rather than straight up? Well, what I did was notice that my X values are really not changing very much at all. In fact, right, I have a slope of 0. So my X values are changing very little at the beginning, but my Y values are changing at a rate of about 1. So Y is changing faster than X. And so that's going to force a curve that that has this type of concavity. As I move from pi over 2 to pi, my X values are continuing to decrease, right? So my X value, right now my X value is 0. My X values are continue to decrease to -1, while my Y values, they're going to start decreasing now. They're going to decrease to 0. So X values decrease to -1, Y values decrease to 0. Here's my target point over here. And we wind up with something like that. Now, another thing I want to point out is whenever we draw the graph of parametric equations, we typically indicate the direction of motion that we're moving in as the values of our parameter increase in value. So I'm going to put a little arrow on my graph to indicate that direction. Continuing on, so we're at pi right now. Theta is pi. And from here, my X values are going to increase to 0. Right now they're at -1. They're going to increase to 0, while my Y values continue to decrease to -1. And then finally, my X values are going to increase to 1, while my Y values increase to 0. Right, and I wind up with a circle. Okay. Let's do another example. Let's do a very similar one. Right. Let's just change the roles of X and Y here. Let's let X be sine of theta this time and Y be cosine, and see what changes. So now I'm going to start. X is going to start at 0, while Y is at 1. So let's see. X is 0. Y is at 1. So I'm going to start here. And we're going to begin, let's see, on this first interval. Let's put some angles here. So this is going to be pi over 2. This would be 3 pi over 2. So those are the values of the parameter. And starting here, and my x's are going to increase while my x's increase to 1 while my y's decrease to 0. So x's are going to increase to 1 while my y's decrease to 0. Right, and again, I know that that's going to be the type of concavity of my curve because x now is changing at a faster rate than y is, right? Y is changing at a rate of 0, instantaneous rate of 0 when we begin. And so my vertical distance is not going to be changing much, but my horizontal distance is going to be changing more. And so that's going to force that sort of a curve. And this is the direction I'm heading as I move from 0 to pi over 2. And then as I move between pi over 2 and pi, x's now are going to decrease to 0, and my y's are going to continue to decrease to -1. So my x's are going to go this way, my y's are going to go this way. My little Etch-a-Sketch, right? So I'm going to be decreasing both of them, and that's going to give me that sort of a curve. It looks like I missed there. Now I hit it. That's at pi. And now x is going to decrease to -1 while y increases to 0. So x is going this way, y is going this way. Here's my target. And we get this curve. And then finally, x is going to increase to 0, y is going to increase to 1. And I've got another circle of radius 1, but this time the direction of motion is reversed from the other example. Okay, let's do one that doesn't involve trig functions this time. Let's let x be, change the name of the parameter, doesn't matter what I call the parameter. X is the cube root of t, y is 1 minus t. I have those two graphs sketched below. So let's pick a starting point. Looks like this might be a good starting point. I know the value of x and the value of y whenever the value of t is 0. Right. Notice, by the way, I don't know if this occurred to you, but I'm not labeling this axis because I'm using it for both x and y. Right? Whenever I'm paying attention to this graph, I'm thinking of this as values of x. Whenever I'm looking at this graph, I'm looking at this axis as representing values of y. But I'm doing this simultaneously. Okay, so whenever x is 0, y is 1. So let's indicate that. Whenever x is 0, y is 1. And so 0, 1 is going to be a point on our graph. And now let's see what's happening. So as t increases in value, looks like x is increasing. Actually, x is increasing at a very, very rapid rate, right? In fact, it's, the slope there is infinite at this at 0 for the x graph. So x is increasing very rapidly, but only rapidly for a very short amount of time, and then it tapers off in the rate at which it's changing. Y is changing. Y is going to be decreasing at a constant rate the whole time. So let's see, how are we going to indicate that? So x is moving toward, well, let's see, I guess this would be whenever the value of t is 1, x is also going to be 1. So we're moving toward x being 1, y being 0. X being 1, y being 0. So we're moving toward that point, and we're going, let's see, we said that y is not changing very fast, but X is changing quite rapidly. And so that's going to have this effect. Let's see, so X is changing quite rapidly at first. Y is changing relatively slowly. So I'm going to have that sort of behavior. And then as I move away from t being 1, my x's are continuing to increase, but not very quickly, and my y's are continuing to decrease, and they're going to be decreasing faster than the x's eventually. So that's going to look something like this. And as t was increasing, my curve was moving in that direction, so indicate that with that arrow. It should probably have been a little bit, right, since x was increasing infinitely quickly there, I should have a horizontal tangent line at that point. And then let's go back to that point. So let's see, back to whenever t was 0, and go the other direction. So whenever we go backwards, x is decreasing in value. So as we go backwards, x is going to be heading this way, while y is heading upward. Again, x is changing very rapidly at that point, so that's going to give us a horizontal tangent line there. And our y's are going to eventually increase faster than our x's do, and so we're going to have a curve that looks something like that. All right, so that would be the graph of this pair of parametric equations. I want to do something else with this particular pair of parametric equations, and that's a technique called eliminating the parameter. Sometimes this is useful, sometimes it's not even possible, but what that means is to rewrite this in terms of x and y, eliminating the parameter t. And that's relatively easy in this particular case. What we have is that, let's see, so this says that y is equal to 1 minus t, but t, I'll go ahead and write the t there, but t, let's see, if x is equal to the cube root of t, that tells me that x cubed is equal to t. So in place of t over here, I'm just going to write x cubed. And so this equation in x and y describes the same graph that that this pair of parametric equations did. And you know, if we go back up here and look, this does look like, doesn't it? This does look like if this point were down here, that would look very much like the opposite of x cubed. And adding 1 to that bumps us up 1. So that's a nice little check that our equation or that our graph is what we in fact have drawn. Let's look at another example. Let's go back to another trigonometric example using trigonometric functions. This one's just a little bit more complicated than the ones we were looking at before. So this time x is sine theta, y is 3 times cosine theta. So again, pick a starting point. Looks like, so this is our x, this is our y. So a good starting point would be whenever x is 0 and y is 3. Here we go, x is 0, y is 3, so this is going to be a point on our graph. And then let's see, so now as we go, as theta, this is my theta axis here. As my theta goes from 0 to pi over 2, my x's are increasing to 1, my y's are decreasing to 0. My x's are increasing to 1. My y's are decreasing to 0. So I'm going to go from this point to x goes to 1, y goes to 0. So I'm going to be heading toward this point right here. And let's see which one's increasing faster. The x is increasing faster than the y. I have a slope of 0 here at the for the y graph. So y's are not changing very quickly. My x's are changing more rapidly. In fact, my y's have a slope of 0 at this point. So I'm going to have a horizontal tangent and heading toward this point. Put the arrow on there to indicate the direction as my theta values were increasing. And keep going. So pi over 2 to pi, my x's are going to come back to 0 while my y's go to -3. So my x's are going this way, my y's are going this way. I'm heading toward this point. Right? Between pi and 3 pi over 2, x's are decreasing to -1, so my x's are heading in this direction. My y's are increasing to 0, and I'm heading toward this point. And I'm heading toward the point where x is -1, y is 0. X is -1, y is 0 is right there. So there I go. And then continuing on, my x's come back to 0 while my y's go to 3. And we have what appears to be an ellipse. All right. How would we eliminate the parameter for this particular set of, or this particular pair of parametric equations? Well, there are a couple of things we could do, some neater than others. If we just kind of blindly do what we did in the previous example, we could say that, well, we could say y is equal to 3 cosine theta, and use our equation over here to recognize that theta is in fact the arcsine of x. And so we could eliminate the parameter by simply saying that y is equal to 3 times the cosine of the arcsine of x. And we've done it. We've eliminated the parameter. We have an equation in terms of x and y. There's kind of a cleverer way of doing this. Recall in our very first example, whenever we were looking at the circle, we used the fact that cosine squared of theta plus sine squared of theta was 1. Well, I'm using sines and cosines here as well. And what I have is that sine of theta is x. I have the cosine of theta is y over 3. So since I know that sine squared theta plus cosine squared theta is 1, just with a little bit of algebraic manipulation, I can write that x squared plus, let's see, this is going to be y over 3 is cosine, so y over 3 squared, that's going to be 1. And so this equation, in terms of x and y, describes the same curve that I graphed over here. With that in mind, can you find a pair of parametric equations which generate the graph of x squared minus y squared equals 1? So we're kind of going in the opposite direction now. right? I'm starting with an equation in terms of x and y, and I want to see if I can find a pair of parametric equations whose graph is going to be the graph of this function. I want you to think in terms of trigonometric functions. So that's your hint. I want you to pause the video for just a moment and see if you can come up with a couple of trigonometric functions, which is going to do the job here. Okay. Let's see if what you did agrees with what I did. There are a couple of ways we could have proceeded, right? But I'm going to go back to sine squared plus cosine squared equals 1. Of course, that's not going to help us a whole lot in that form. But if I divide both sides by cosine squared, then I've got tan squared theta plus 1 equals secant squared theta. Well, subtracting tangent squared theta from both sides puts me in the same form that that my equation in x and y is in, right? A thing squared minus another thing squared is 1. So how about if I let x be secant theta and y be tangent theta? Actually, this is not what I meant at all, right? Let's let x be secant theta so that y be tangent theta. And then what we've got is that x squared minus y squared is, well, if x is secant theta, then x squared is secant squared. And y squared is tangent squared theta. But I know that that's always equal to 1. And so this pair of parametric equations ought to give me the same graph that this equation gave me in terms of x and y. Now, we haven't talked about how to use technology to graph graphs of parametric equations, and this might be, I think, a good opportunity to see how to do that. So I've got my TI-84 here, and if you have one, I suggest you go get it. Pause the video for a moment, run and get your calculator. Okay, so probably right now, if you were to go to your window that allows you to input functions, probably you have it set for y equals, and then it's expecting a function in terms of x. And in fact, the default variable is x if I hit my variable button there. But what I want you to do is change the mode. Here's your mode key. Change your mode. Come down until where this line where it says func, par, pol, seek. Well, change it from function notation to parametric notation. Quit out of that. And now let's go back to our y equals key. And notice how it's changed. Now, instead of just having y equals something, we have an x and a y equals something. And that's because it's expecting a pair of parametric equations, one for x, one for y. So let's go ahead and type in what we did here. Let's see, x is secant theta. Let's see, we don't have a secant key. That's 1 divided by cosine, isn't it? So I'll do 1 divided by cosine of theta. And so now whenever I hit my variable key this time, instead of x being the default variable, it changes it to t. I wrote theta here. Doesn't matter what the parameter's called. T is just fine. So that's our x. Our y is tangent theta, so we can type that right in. Tangent of t. And let's hit graph and see what happens. Look at that. So we get a hyperbola, which you might have recognized was exactly what this equation describes. A little bit of coordinate geometry knowledge might bring that back, that that equation is going to generate a hyperbola. And that's exactly what we got with this pair of parametric equations. Now, while we're here, we might notice that the window that we use might be important. Here, my t-values were going all the way from 0 to 2 pi, which were enough to take us through enough of the graph of this function that we could see what was going on. But if I didn't actually have it going that full range, if I only had, say, it going from 0 to pi, let's see what would have happened to the graph. Right, we would have only gotten part of it. So you need to be careful about what the range of your value of t is. Another thing to take note of, let's go back there again, is this t-step. Now what this is indicating, it's set at 0.1 right now, that means that the calculator is going to, well, it's going to start at 0, and then it's going to make another calculation for 0.1 radian, and then 0.2 radians, and so on. If I'm not paying attention to that, if t-step were, say, at 1, now it's just going to calculate at 1 radian, at 2 radians, at, well, 0 first, and then 1 radian, 2 radians, and so on. Watch what that does to the graph. Right? So it's calculating a value at one point, at another point, that are far apart, right? And 1 radian is a pretty big distance. And so we want to make sure that this t-step is sufficiently large or sufficiently small to avoid that. If I make it too small, let's look again at what happened whenever it was 0.1. It graphs it pretty rapidly. If I had changed that to, say, 0.01, well, now it's going to make a calculation every 1/100th of a radian and plot the corresponding point. So it's going to do 100 calculations instead of just, I'm sorry, it's going to do 10 calculations for every calculation that it did at 0.1. So that's going to have the effect of slowing this down, right? It's doing more calculations as it sketches the graph. Now, that might have the effect sometimes of a more accurate sketch, but graphs on calculators are pretty pixelated anyway. So I usually like to keep my t-step at 0.1. It's a pretty good compromise. Okay, let's continue. I'd like to end with a question. How many pairs of parametric equations can you find which generate the graph of y equals x squared? Well, I'll tell you what, let me write down the most obvious one that I can think of, and that would be letting x be t and letting y be, well, let's see, if I want to graph y equals x squared and x is t, then I would want y to be t squared. That should do it. Let's check it out with our calculator. Let's see. So let's change the let's change the function. And so here, let's just put in t. Here we'll put in t squared. And that ought to do it. Let's see, we'll sketch the graph. Well, that's interesting. It does look like a part of what we expected, right? We expected a parabola, just a standard parabola with vertex at 0, 0. We only got half of it. Why? The window. Our t values are going from 0 to pi. And so my x values are only taking on values between 0 and a little more than 3. So I'm not getting anything for my negative x values. I'm going to have to change that. So let's go back to the window. I want to pick up some negative values as well. Let's go from negative, let's say we go from negative 3 to 3. And we better check our x values here too. Let's see. So I guess the window was showing us values of x between negative 3 and 3. It's showing us values of y between negative 2 and 2. We could probably play with those a little bit, but I think we probably have enough to give us, yeah, we got the sketch of the parabola right there. Let's see if we can think of another pair of parametric equations which are it's going to generate exactly the same graph. Well, if you think about it for a moment, it looks like x could be just about anything. Let's try, I don't know, let's let x be, how about let's let x be t squared. And we'll let y be, well, let's see, we want eventually y to represent x squared. So if x is t squared, y is going to have to be t to the 4th. Does that do the job? Well, let's look at it. So I'm sorry, y equals. So we'll let this be t squared. This is t to the 4th. And we'll graph it. Oh my goodness, again, it looks like we only have half of the graph that we expected, half of the parabola. Why is that? Well, we could go back and check our window again. Well, our values of t are taking on negative and positive values. Oh, but t squared is always a positive number. So if x is equal to t squared, then x is always positive. So I'm only going to get points on the parabola that have positive values of x whenever I use these two. So what we're seeing is it looks like we could let x be absolutely anything and y be, well, the square of that anything. And what we're going to get is, well, at least some of the graph of y equals x squared. But it's going to depend on which values of x are possible with the function that we choose for our anything, right? If we, this is an interesting one. What if we would let x be sine of t? Well, then y would be sine squared of t. What's going to happen this time? What values of x can we get from sine t? Well, sine t takes on values of x between negative 1 and 1. That's it. So we wouldn't expect very much of the parabola to show up. So if this is sine t, and this is sine of t quantity squared, then I should only get a small little bit of the parabola. And there it is. And in fact, let's see, there's a setting on here. Let's see if I can find it. So if I go back to the y equals again, and notice this little line over here. I have a solid line in that little position. There are other things that I could have there. Let me cycle this back and forth. Whoops. Let's see, how do we do this? Is it with the enter key? Yes. So the enter key changes that little coordinate, or that little symbol. And if I change it to this little circle-like thing, and then I do my graph, it's showing me how the graph is being created. And look at that, it still wasn't done. It traced back over itself again. And if I change my values of t, let's do a whole bunch more. Let's go between negative, I don't know, let's go between negative 10 and 10 this time with my values of t, and see what happens to my graph. Well, it's going to sketch exactly the same part that it did before, but it's going to sketch it over and over again as the value of t goes between negative 10 radians and 10 radians. And it should stop here pretty soon. There, all done. Okay. So that is that's our discussion on additional examples of parametric equations. If you'll do the homework for this section, I'll do it as well, and I'll post my solutions for you, and you can check your answers. I look forward to seeing you next time. Whenever we go back to, we're going to revisit the cycloid again and talk about a lot of questions, calculus type questions that we could ask and answer about the cycloid in terms of parametric equations. Until then, stay well, stay healthy. I'll see you then.